Good evening, everybody. Welcome to the Open University. This is the Open STEM Labs at the Open University. I'm Dave Rothery, Professor of Planetary Geosciences and the Chair of S283, the Planetary Science Level 2 course, and the lead educator on the FutureLearn Moons MOOC. So hello, whether you're a 283, 282, Moons MOOC learner, or anybody else associated with planetary sciences. With me in the labs tonight is Rachael Hamp, who you'll be meeting very soon. We had hoped to have Helen Fraser, the chair of S282, but circumstances have got in the way. So Helen sends her apologies and won't be joining us, but we have plenty of expertise here anyway, don't we, Rachael?
Of course, Dave.
We often start with a little bit of news. What's been really exciting this year for me is the flyby that NASA's New Horizons spacecraft did of MU-69, a Kuiper Belt object quite some way beyond Pluto. It sent back some rather low resolution images to begin with, but we've got really nice resolution pictures now. This is probably the highest resolution picture we're going to get of MU-69. So this is an icy body. It's about 30 kilometers end to end. So the lobe on the right is about 18 kilometers. The lobe on the left is about 12 kilometers in size. It's a contact binary between two lumps of largely icy material that must have come together slowly enough that they didn't fragment, but hard enough that they got stuck together. But what happened before that? I mean, look at the big lobe on the right. Can you see individual components? Does it look like lumps that have got squished together and stuck together somehow? So more violent but non-disruptive collisions to begin with, and then the lower energy, slower collision of two such objects to give the contact binary. It's quite an eye-opener. I mean, everybody's puzzling over this. So what a wonderful object. And the small craters you can see along the belly of the snowman, if that's how you see that shape, they're craters well below a kilometer in size, a few hundred meters across. We're seeing a lot of detail here, so that's a great picture. That really excited me. But talking of icy bodies, Rachael works on one of the most exciting icy bodies in the solar system. Now, Rachael, you're a second-year PhD student here now.
Yep.
So please tell us what you do.
Yeah. So I study Enceladus, which is one of the icy moons of Saturn. Enceladus is actually it's classed as a mid-sized moon, but it's actually quite small. It's only 500 kilometers in diameter. So what's really interesting about Enceladus and why a lot of us study it and why we think it's interesting is that Enceladus actually has a global subsurface ocean, which means there's a surprising amount of liquid water on it. So as you can see here, the ocean goes the entire way around that rocky core. You'll be able to notice that it is deeper on the south polar region. This is also in an area of high heat flux. So where the rock and the water interact here, there's expected to be some kind of hydrothermal systems, a bit like black smokers that we get on Earth is what is thought to occur. And then recently, these plumes that you can see being ejected out of the South Polar region have actually been studied by the Cassini mission. And Cassini has detected some of the bioessential elements that we need for life within these plumes. So on Enceladus, we've got liquid water, a source of energy, and these bioessential elements.
So the source of energy is tidal heating, which is the difference with Earth, yeah?
Yeah, so you've got a tidal heating, which is keeping that subsurface ocean warm and keeping the water in liquid form. But Cassini has analysed the plumes on Enceladus 8 times using mass spectrometry and an instrument known as the Cosmic Dust Analyzer.
This is because it flew through the
plumes.
plumes.
So it's flown through the plumes brilliant. 8 times in total. So what this means is that we've actually been able to analyse the composition of the subsurface ocean without having to land on the moon and drill down. It's very conveniently throwing the subsurface ocean into space for us.
Yeah.
So that's why it's really exciting and why it's really interesting. So what I personally am doing for my PhD is I'm trying to define a carbon cycle in the subsurface environment. So carbon is one of the bioessential elements, and it's crucial for life as we know it. So understanding how carbon moves within that subsurface environment is very important. So
there's a graphic, isn't there?
Yeah. So for what I'm doing for my project is I'm focusing on what you can see in the bottom right-hand corner of this diagram. So I'm basically trying to recreate where the rock and the water meet, and trying to recreate this in a lab. So we've got information from these plumes of what the composition of the water is, and this is as the rock and the water interact, that's going to change the chemistry of the ocean, which is what we've analysed. So from using this and working backwards, we've basically taken an educated guess, basically, Dave, at what the composition of the rock is. So what I've got
That's
here,
what you've got here,
exactly,
right?
Is all of the different mineral components that I'm going to be putting into my simulant to recreate the rocky interior on the subsurface ocean.
So you're going to grind these up?
So yeah, I'm taking all of these, I'm going to grind them up so they're all the same grain size. And then what I'm going to do is, once this is all ground up and it'll all be, mixed together into one big powdered form, can mix it in with some, with a fluid to represent the chemistry of the subsurface ocean, and then in a high temperature, high pressure reactor system that we've got here, recreate the conditions we expect at the rock-water interface. And through the changes of the mineralogy that we've got going on here, and the changes of the chemistry in the subsurface ocean, we'll be able to get an idea about what geochemical cycles are happening.
So what mineral components are you putting into your
what we've got here
simulant, and
is
why?
the one that I don't have here, which is actually the major component, is olivine. It's currently being crushed in the lab.
Okay.
So I've also got magnetite here, which is
iron titanium oxide.
It's essentially just an iron oxide.
Okay.
And then we've got serpentine, which
it's a magnesium silicate, slightly hydrated, isn't it?
Yeah. We've got dioxide.
It's kind of pyroxene. That's another magnesium or iron silicate.
So we've got, and then the rest of these others are in much lower quantities. So we've got anhydrite.
Calcium sulfate.
You're good at these, aren't you, Dave?
Yeah, I'm a geologist.
We've got some quartz, so not overly exciting.
Silica.
And some talc and some pyrite.
That's an iron sulfide. So
that's
that's rather
sulfide.
Different to the others.
Yeah, and sulfur itself actually hasn't been detected within Enceladus. But I'm basing this chemistry upon a Ci chondrite, so a carbonaceous chondrite, and the Ci is just the most aqueously altered one.
And there are sulfides in these meteorites.
And there are.
So, okay.
And it's widely thought that there could be sulfur and sulfides on Enceladus. They just haven't been detected yet.
Okay, there's no carbon in anything you've shown me.
No, so well spotted, as I am looking at the carbon cycle. So at the back here, I have different carbonates. So we've got calcite, magnesite, and dolomite.
So that's calcium carbonate, magnesium carbonate, and a mixture of calcium magnesium carbonate.
Yes.
Okay.
So these are my inorganic forms of carbon. And then last year, macromolecular organics were detected within the plumes of Enceladus. So this is large organic structures that have been detected in the plumes of Enceladus, which is incredibly exciting because it hopefully means that some cool chemistry is going on.
Like you say, macromolecules, these are what, 20 carbon atoms linked?
So
how many?
We're looking at greater than 200 atomic units.
Greater than 200 atomic units, and carbon mass is
12.
Okay.
So it's thought to be lots of essentially benzene rings, which are connected through functional groups rather than long carbon chains. But each benzene is like a separate unit in itself, then connected through functional groups.
Okay, so are you trying to manufacture these macromolecules, or are you going to put them into your mix and see what happens?
So the paper that came out last year talking all about the macromolecular organics, have basically determined that it's a bit like humic acid. So I'm just going to put humic acid in. And so humic acid is what we find in soils on Earth. So it's a naturally occurring organic product on Earth. But hopefully by putting that into my simulant, as well as the different carbonates, and we can see then how the chemistry cycle and whether or not these organic molecules stay together or whether or not they're all going to do some cool chemistry.
Well, is the driver for this cool chemistry, or is it because people think that where you've got hot chemically charged fluids coming into the ocean, that would provide an energy pathway for life to exist?
So, I mean, the main reason for this is because obviously by understanding what carbon cycle is going on, we can understand what different chemical species are available to be used by microbial life. So there's a group of astrobiologists here that will basically take my project and just further it on one step. And they're going to see what microbial life could exist through the different chemical processes that I determine here through these reactions. So they'll basically just take what I've done, my little reactions, and put microbes into it and see if they survive. But the big point of all of this is to answer whether or not Enceladus could be habitable.
Yeah, do you think it's a better bet than Europa?
From what we know so far, we just know more about it. So for what we can currently work on, we've got more information for Enceladus. I really like Europa, and Europa has a lot going for it in terms of it being more habitable, mainly that it's a lot larger.
Yeah.
So Enceladus could be very, very young, and the fact that it's so small means that all the chemical reactions could be used up, and it could just get into quite a boring, nothing exciting happening, which in terms of life isn't going to be great. Whereas Europa I believe Europa is just a tiny little bit smaller than our moon.
Yeah.
The size of that just means it's more feasible in the terms of its size, but we obviously don't know as much about it yet. But obviously there are a couple of missions going soon. So I'm sure once we understand more about Europa, we'll... I
mean, they're both good targets. Those of you who've played Moon Trumps, you can see Europa on the wall behind me over there, and Enceladus now. They're the top two Moon Trumps cards to have if you want potential for life. I think we're probably right when we came up with those numbers.
I think so.
Okay, I'm sure we'll come back to Enceladus. I don't see any online questions via the widget. Please do post questions in if you want to ask us some. But we did have plenty in advance, so we'll make a start with those. Okay, in the OU's Physics, Astronomy and Planetary Science Forum, John Hutchison asks, Enceladus is obviously a high priority target for future missions given the wealth of data from Cassini and the exciting possibility of conditions that might support microbial life. Are we likely to get further information from Cassini or other existing missions, and what sorts of missions are being mooted? Is there anything still to come from Cassini, do you think?
So we're not entirely sure. The Cassini team are keeping everything that they know and anything that they're working on quite close to their chest. Yeah. They're not really saying if they're working on anything. So the paper about the organics only came out last year, and until it came out, it was mentioned at a conference, and that was it. It wasn't known it was working on. So when it came out, it was quite a shock to most people that was something that had been found. So whether or not they're still working on data and how much more is still left to come out, they haven't really said, but I imagine most of it has come out now, and I'm not entirely sure what else could come out from the data.
But there are future missions that may happen. What can you tell us about those? So
for Enceladus, there are no definite missions to go. There are a few proposed ones. So my favourite is ELF. So ELF is Enceladus Life Finder. So it is basically to do exactly what it says on the tin. The aim is to find some life. How? Well, ELF, I believe it wants to fly through the plumes and detect biosignatures, and so Cassini wasn't set up to detect any biosignatures. It wasn't set up for Enceladus. It was set up for the entire system of Saturn. It didn't expect to find everything that it found. So it's basically just going back, but with instruments that are there that are specified for Enceladus. We've also got NX, which is the Enceladus Explorer. And this is going to be an orbiter and a lander.
Okay.
And then there's a few missions that link Enceladus and Titan together, being the two most interesting moons of Saturn.
But these are all at the stage of being funded as
so they're all
study.
They're all hypothetical
Yeah.
missions, none that have been accepted.
So we will be back to Europa.
So we will be at so Europa Clipper.
That's the NASA mission.
That's the NASA mission, and then JUICE is going, which will fly by Europa on the way to Ganymede, and that's the European Space Agency mission.
And we have colleagues on the team for that.
We do, yes.
We do. Okay, that's great.
So, well, I have got a question here for you, and this one has come in from a learner on the Moon's MOOC. And this is a question that says, what new insights can we expect from the Chinese mission to the dark side of the Moon?
Okay, thank you for that question, Annette. Maybe you're a Pink Floyd fan. We don't talk about the dark side of the Moon because it doesn't have a dark side, but it's on the far side of the Moon, the side of the Moon that never faces towards the Earth. It's metaphorically dark, but not physically dark. I'm sure you know that. I try not to let people talk about the dark side of the Moon because it gets just as much sunlight as the near side. So the Chinese have a lander landed round about the turn of the year called Chang'e 5, and it landed on the far side of the Moon where nobody had ever landed before. This is a hemispherical view of the far side, and it looks a bit different to the near side. There are very few dark patches, no large dark patches. There are many areas of the Moon's near side flooded by these mare basalts, giant flood basalts. That's hardly occurred on the far side of the Moon. There are some basalts on the floors of some of the craters. So the Chinese sent a lander there, and if we zoom in to a view of where they did land, it was in the large crater near the centre of the view there, the crater that's about a sixth of the width of the field of view. That's a crater called von Karman, and they landed on the south part of the floor where it's smooth because it's flooded by basalt. So they're not landing on anything that you perhaps couldn't see on the near side, but they landed somewhere smooth because it's safe if it's smooth. But even though they're on the lava plains, there will be material that have been thrown in onto those lava plains from the smaller craters outside. So we hope the lander will be able to sample material that has come from the highland crust outside the crater. And if anybody thinks it might be a hoax and the Chinese are only pretending to have landed on the far side of the Moon, their spacecraft has been imaged on the surface by NASA's Lunar Reconnaissance Orbiter. Now, this is a view looking north across von Karman crater. There are a couple of tiny arrows towards the lower right that are converging in on a single pixel in that image. And that is the Chang'e 5 lander on the Moon's surface being imaged by NASA. So they got there, it's true, there's no conspiracy here. And there's a rover and a lander, and we've got a couple of pictures. We've got a picture of the rover seen from the lander. That rover is called U2-2 because the previous lander was just called U2. And we've got a picture from U2 looking back at the lander. And there are various scientific instruments on board these, mostly on the rover. There's a radar to measure the depth of the regolith. There's some relatively restricted geochemical analysis that can be done. And they've only gone a few tens of meters so far. It survived 2 or 3 lunar nights. It could go on for months and hopefully years. And let's wait to see how far it goes. And hopefully they can find some material that has been thrown into von Karman from a younger crater outside. But the main scientific breakthroughs that we're going to get from this mission, well, I don't think the scientific breakthroughs are the big thing from this mission. I think it's the technological achievement. To have landed on the far side of the moon for the first time, and to have landed something quite big on the moon, because that was a big landing craft we saw. You could have put a crewed vehicle on top of that, along the style of Apollo, and the Chinese are working towards sending humans to the moon. But to get to the far side, they had to prepare the way, because if you're on the far side of the moon, you can't communicate back to the Earth because you've got no line of sight for your radio signal. So back in July last year, the Chinese put a spacecraft in a fairly fixed position above the far side of the moon. And the next graphic shows that. This is a diagram showing Lagrange points. Imagine M1 is the Earth and M2 is the moon, and these things labelled L1 through L5 are the Lagrange points. They're the stable or quasi-stable points when you've got a large body orbited by a smaller body. And the Chinese relay satellite called Kuiyao is stationed pretty much at L2, the Lagrange point beyond the moon on the Earth-Moon line. And their satellite is orbiting that Lagrange point, and it can stay there more or less indefinitely, and it can see down to the moon's surface. And you'd think exactly at L2 you wouldn't see to the Earth, but it's orbiting around L2, and it has got a permanent view of the Earth, as you can see in the final graphic. This is a real picture from the relay satellite. The moon is near to the satellite, which is why it looks big. Mm-hmm. The Earth is in the distance, but it's permanently above the lunar horizon. So the relay satellite can get the signal from the lander on the surface, which will be somewhere down in the 4 o'clock position in that view, up to relay satellite and back down to Earth. And of course, commands from the Earth come the other way. So putting that relay satellite into position allows direct communication between the Earth and the far side of the moon. So for me, that's the Chinese great achievement that's come out of this mission. And well done them. And watch this space. They're going to do a sample return mission somewhere on the near side this year, I think, probably. And they'll have humans on the moon within 3 or 4 years, I should think. Have we had any?
We've had a question, but you answered it as you went along. It was a question about how the signal got back from the far side. So.
Okay, I've already preempted you there, Julian. Okay, what else have we got? Rachel, there have been a lot of advanced questions about Enceladus. Here's one on the moon's Facebook group. There is a Facebook group for moons that was set up by the learners on the moon's MOOC. Steve Jack is asking, as the light energy from the sun is about 100 times more on the Earth than is out on Saturn's moons, do you think there's enough light energy to support photosynthesis near the surface of Enceladus, where the cracks exist?
So that's a good question. So that's looking at not the same kind of microbial life we were talking about earlier. So in terms of photosynthesis, if you're looking at the subsurface ocean itself will be in complete darkness because the ice crust is a minimum of 5 kilometers deep, 5 kilometers thick. So any form of sunlight isn't going to be able to penetrate through that. So the subsurface ocean itself is going to be completely dark. But the question was about the ice cracks themselves. So yeah, the cracks on the South Polar region do go obviously from the surface into the subsurface ocean. And these are expected to be, I think they're thought to be about 2 kilometers wide. So
it's pretty wide, but
pretty
even
wide.
So.
But the issue is that they are on the South Pole, which means that any sunlight that is going at Enceladus, it's never going to travel straight through the cracks. So you're not actually going to be able to get any sunlight travel down those cracks. And even if you were to get a very slight amount, they're not expected to, be direct straight lines to be very ziggy-zaggy. Yeah. So actually going down the cracks themselves, it's not expected that there would really be any sunlight. So unfortunately, photosynthesis probably isn't likely.
Yeah. The limiting factor for photosynthesis isn't the faintness of the light. Photosynthesis can go on at quite faint light levels. It goes on at the Earth on cloudy days. So there would be enough sunlight there if other conditions were favourable.
There would be upon the surface of Enceladus, but obviously on the surface it's not going to be feasible for other reasons.
Yeah.
But either in the subsurface ocean or down those cracks, unfortunately, there's not going. It's just going to be complete darkness.
Maybe, Steve, on Europa, where sometimes the ocean is exposed to space, or the cracks are equatorial, there's more chance of the sunlight shining straight down. People have suggested a photosynthetic ecosystem in the tidally opening and closing cracks on Europa.
Yeah,
it's more likely than in
also on Europa, you've got the subsurface lakes trapped within the ice crust, which are quite close to the ice surface. So, but they are themselves full of lots of tiny little cracks.
Yeah. So Enceladus isn't the place for photosynthesis.
Unfortunately not.
Okay. Still no live questions. So, Rachel, there's one here from an S283 student, Nigel Patterson. He says, bearing in mind that giant exoplanets are easier to detect than terrestrial exoplanets, are there any theories as to relative preponderance and distribution of these in the universe? That's not really your bag, is it?
I think that's a question for you, really, Dave, not for me.
Yes, Nigel, if you're studying S283 now, as I believe you are, you'll be coming on to the exoplanet chapters very soon. Giant exoplanets are indeed much easier to detect than terrestrial-sized exoplanets, but we have got plenty of Earth-sized planets detected now. What we're missing in this solar system is mini Neptunes, things smaller than Neptune, but a lot bigger than the Earth, which we find in great numbers elsewhere. But we're still working on the statistics of what we should get. But the strange thing is that the first exoplanetary systems that were discovered tended to have Jupiter-sized bodies really close into the star, hot Jupiters that have migrated inwards. And we've learned a lot about how planetary orbits can migrate.
Okay.
So we are still trying to work out what a typical solar system is. Ours isn't typical, but it's not wildly unusual either. And another strange thing we found recently about extrasolar planetary systems is that red dwarfs have lots of planets as well. We didn't expect there to be planets around dwarf stars. These are stars that have enormously long lifetimes, but the habitable zone, where conditions are suitable for life, because the surface temperature is above 0 and below 100, that zone is really close to the star. And those planets would be in captured rotation, so they only keep one face to the star all the time. So there is no typical planetary system, but we're not particularly unusual. And Nigel is asking about theories about the relative preponderance. Well, we're still collecting the data, really, but we do know that orbits can change quite considerably.
All right, I've got another question here for you.
Okay.
And this is from Leslie Andrews on the Moon's Mook. And this is a question about Io.
Yes.
Whether or not there is any chance that the other craters are linked to the volcano showing lava, or would this be visible somehow? And could there be larger channels of lava underneath the area, or is it isolated? And finally, as the lava is hot, can it be tracked under the ice exterior of the planet by heat sensory means?
Okay.
It's a lot for you there, Dave.
Yeah. Leslie is talking about a picture that's in the Moon's Mook, but it's also in Introduction to the Solar System. It's this picture here. That's largely a visible image of an area of Jupiter's innermost large moon, Io. That field of view is a few 100 kilometers across. The yellow color is sulfur and sulfur compounds on the surface. The black areas are more like fresh looking rock. And what catches the eye is the glowing red-orange area on the left-hand side. And that is an active lava flow that's radiating very strongly. But this image is a composite, and what's glowing there on that long red-orange streak is actually infrared light that's been superimposed on that view. And the only actual visible glow is the 2 points of light at the very tip of that lava flow where it forks, and that's lava breaking out to the surface and radiating really, really strongly. Now, Leslie's asking about stuff connected underground and so on. I don't think that the caldera in the middle and the caldera at the top, those black lava patches, have a horizontal channel going between from one to the other or linking it to the lava flow. That lava flow is coming from a volcanic vent just out of view to the left. But it's a volcanically active area. There are lots of vertical pipes feeding magma from the interior of the moon. Now, this particular picture was from 22nd of February in the year 2000. We've got a view from 3rd of July the year before, 1999. That's more or less the same area. You can see that kind of curvy Y-shaped lava flow at the left, nothing glowing on that. But what is different here is that red area in the middle. And that's actually visible light. There's no superimposed infrared here at all. What you're seeing is a fissure in the ground with a fire fountain erupting. And the left-hand part of it is just stuff thrown into the sky and falling back to the ground. The little tongue coming towards the viewpoint at the right-hand end is a lava flow on the surface. So that was going on before the previous image. I don't know if we can go back to the previous image. If we can, you'll be able to see that lava flow, see where that lava flow is. It's a 6-month-old lava flow there and no longer progressing, that small one coming from the fissure. So there are changes going on here. Now, Leslie also asks about stuff connected underground and can we track it under the ice exterior? Well, there's no ice here, Leslie. Io is the only large moon of Jupiter not to have an icy surface. Because it's been so volcanically active, all the water has been lost to space, and the volatile that's involved in the volcanism is sulfur and sulfur dioxide. But it is icy temperature when you're away from the volcanic areas. Infrared will see stuff at the surface, or it will see a lava flow that's got a crust developed over it. But if you've got something 100 meters down, it's not going to give a strong enough signature to see. So we don't use infrared to see underground. It really is for looking at things going on at the surface. But that's a nice example of what you can do with infrared and indeed the visible glow on Io. People are tracking volcanic eruptions on Io with telescopes on Earth right now. You need to be above the atmosphere, most of the atmosphere, so you can see the infrared properly. So there's an observatory in Hawaii which does a good job of this, for example. We've had a question on the widget. Colin Fraser says, are the plumes on the moons in very select regions, or can they occur at different regions as the moons orbit? We've only got plumes from 2. There's Europa and Enceladus. Yeah.
So on Enceladus, they are located just on the south polar region. And we're not entirely sure why. It's mainly, that's where the area of high heat flux has also been detected, and where the ocean is deepest. So there's some form of how they initially formed and why they're only on the south polar region. Because in fact on the north pole, the heat flux is higher than anywhere else. Not as high as you find on the south pole, but it is higher still. So the 2 poles themselves have the most amount of water. It's where it's deepest, but it's on the south pole where we've got a lot of water, and it's the only place we find those plumes.
Yeah, whereas on Europa, we only know of Europa's plumes from the Hubble Space Telescope, and they tend to be, they are equatorial.
Yeah, I think if I am not mistaken, they thought they detected 2 plumes, and now they're bringing one of them into question and thought it could have been a fuzzy patch on the top. However, they still think one of them is there, and hopefully, I'm sure Europa Clipper and JUICE will be able to give us more answers.
Yeah, I mean, the Europa Clipper will have a mass spectrometer, and it could fly through plumes if it finds any.
Yes. Yeah.
Europa's plumes are not as persistent.
No, they think they're to be a lot more intermittent, yes.
Yeah. We've had more live questions. Okay, Colin Fraser saying, do the plumes affect the orbits like a rocket engine? No, there's very little mass. Is it 20 kilograms a second coming out of Enceladus? Some such figure. Whatever it is, compared to the mass of the moon, it's not really affecting the moon's orbit.
No, it's not affecting the moon's orbit at all. But what's actually quite cool about the moon, the plumes on Enceladus, is that as it is to eject the matter out of the plumes, it's actually held in orbit around Saturn. So Saturn's E-ring is in fact composed of the subsurface ocean matter that has been thrown out of space through these plumes and then held in orbit around Saturn, as you can see here.
Okay, that's Enceladus, a very bright object embedded in the E-ring.
So Cassini itself has actually managed to measure the composition of the E-ring itself, and all of that is thought to have started from the subsurface ocean.
Okay. We haven't got a whole lot of time left. Let's try and do at least a couple more questions. This one that came in from Eileen Fryer, an S283 student, in chapter 3 of Introduction to Astrobiology, mentions made of dust storms on Mars, but no explanation of what gives rise to them, particularly the ones large enough to shroud the whole globe. How often do they occur and why, and what effect do they have on the Martian climate? And how would equipment and any future human visitors react to such fine dust storms? Well, this question came in an hour ago, so I looked up how to answer it. The dust storms on Mars tend to occur in northern spring and summer, which is when Mars is at perihelion, so it's getting the most sunlight, so more energy to do things to the atmosphere. And big dust storms occur pretty randomly about every year, one Martian year in every 3. The most recent one was last year. It did shroud the globe.
Did a lot of trouble, didn't it?
Well, yeah, some of us are still mourning Opportunity, the Opportunity rover, which was still alive when we wrote this book, but went out of action in about June, July last year, and NASA last month gave up attempts to revive it. Opportunity was killed by dust, making the sky too dark, and probably dust settling on its solar panels, so it couldn't recharge its batteries.
Yeah.
So that was sad. And human visitors. If you've seen The Martian, they exaggerated the force of that storm very greatly, blowing equipment poles so they'd pierce astronauts' chests and so on. The Martian wind blowing really strongly, you could stand up and scarcely feel it because the atmosphere is so tenuous. But there are effects on climate. When there's a dust storm, you've got dust in the upper atmosphere which can absorb the sunlight and warm the upper atmosphere. And that can cause problems to spacecraft that are trying to enter, because if they're relying on the parachute, the warmer upper atmosphere is less dense than expected, so you don't slow down as much as you'd hoped. And also, if ice particles are lofted into the sky with the dust, you're taking water high into the atmosphere, it can then escape to space more easily. So maybe quite a lot of Mars's water vapor, water content, was lost through dust storms lofting ice particles up into the sky. Anything to add to that one?
Not about Mars, no.
Okay. Have we answered a question from Nigel Patterson yet? Nigel Patterson, S283 students, asking about the Kuiper Belt. How far does the Kuiper Belt extend, and how many objects do we believe inhabit it? And is there an official definition as to how big or long-lived an object has to be called a Kuiper Belt object? We've got, I think, a couple of thousand Kuiper Belt objects catalogued. This is observing from the Earth. New Horizons out in the Kuiper Belt has found 1 or 2 more because it's got a telescope on board. But there will be, we've got half a dozen objects comparable to Pluto in size. And there's probably 20 more waiting to be found. And then there's plenty more smaller ones as well. So there are going to be hundreds of thousands of Kuiper Belt objects, Nigel. Just depends how small you're prepared to go. I mean, MU69, or Ultima Thule, if you want to give it that somewhat controversial name that New Horizons flew by, that 2-lobed object, 30 kilometers long. That's very, very hard to see from Earth. and anything smaller than that is exceedingly hard to see. So most of them we won't find until we have a quantum leap in telescope technology or send more spacecraft out there. So there's lots, hundreds of thousands of objects, but the number depends on how small you're prepared to count to. And I'm sure there are Kuiper Belt objects much smaller than MU69. Pluto has moons which have presumably captured Kuiper Belt objects that are about 10 kilometers across. So we do know they go down to pretty small sizes. There was a recent paper published just last week in Science looking at the sizes of craters on Pluto and Charon that would have been caused by objects hitting Pluto and Charon. And from the craters on Pluto and Charon smaller than 10 kilometers in size, they would have been produced by Kuiper Belt objects smaller than a kilometer in size. And it does seem there's a deficit of sub 8 kilometer sized Kuiper Belt objects to judge from the craters we see on Pluto and Charon. So there's some interesting science to come out of the sizes of Kuiper Belt objects, but nobody's defined how small a body has to be a Kuiper Belt object. I mean, people on the moon's MOOC will have been discussing how small something can be and still called a moon,
yes,
as opposed to a ring particle. Yes. Do you have any views on toasters, whether something toaster size counts as a moon or not?
I mean, I don't know where you define from a moon to a moonlet and where the boundary is between those.
Okay, shall we go for one more question?
Yeah.
Pick a question. What do we want to go for? And then we'll wrap up. There's nothing else live coming in.
I don't know if we missed this original.
Okay, all right, we did. Okay, well, this is for you, really, from Barbara Johnson on the Moon's MOOC. She's saying conditions for habitation on all the other planets and moons in our solar system seem highly hostile to life as we know it. Perhaps that's too Earth-centric a viewpoint. What do David and Rachel think is the likelihood of finding life forms higher than microbes on other planets or moons? Give us a chemical perspective.
Well, I think as we briefly spoke about earlier, in terms of Enceladus, I think you would be I think we're only really going to be looking at microbial life. Even though all of the chemistry and all of the chemical components and everything that's required for life is essentially there, the diversity and the concentrations aren't necessarily great enough to be able to host something that's more complex than just microbial life. And then there's also the problems of the age of the moon and how long it takes for life to really form to get to a more complex state. But then there's obviously Europa, which is a lot larger, and it can have these interactions between the rock and the water going on for a lot longer, and the chemistry could probably be more interesting and more complicated. And there's no reason why there can't be more complex life on the moons, but it's not likely. I mean, if we were to find it, that would be incredible. However, I think it's highly unlikely. But I mean, I suppose past Mars, a historic Mars is probably a more likely place where you might have been able to find something that could have been potentially a little bit more complex than microbial life, or it could have been microbial life, or it could have been nothing. You never know.
Yeah, I have hopes of a rich ecosystem inside Europa, because if there are long-lasting hydrothermal vents and you've got microbes, something will evolve to feed on them.
Well, I mean, we have, like we said before, there's black smokers and such things at the bottom of our oceans, and there's loads and loads of species and different life is there, and some of it is very complex. And why, if we have if we have very similar systems on these icy moons, then there's no reason why it can't happen. Yeah.
Okay, I think that's probably it. Thank you for taking part, everybody. My laptop here has gone to sleep, so I can't actually share the widgets with you, but the results of which moon you like best, you're not going to like this, Rachel. It's 43% voting for the moon, only 13% voting for Enceladus.
I'll have to try harder next
You're
time.
in 4th place after the Moon, Io and Europa, and Titan came last.
Well, Titan's pretty cool. I like Titan.
Yeah, but only 4% of the ladies and gentlemen on interweb land like it. Wasn't you like Titan? It's got lakes and waves and
Lakes of liquid methane
magic
on the
islands.
surface. It's cool.
Okay. But thank you for that, everybody. Thank you, Rachel, for giving up part of your evening to come here. Thanks to Kate and Ben in the background. We'll be back for another of these sometime in November, I expect. Even if you're not still studying an OU planetary or FutureLearn planetary or moons course at that point, do join us. If you're at the OU, you keep in touch with the Physics, Astronomy and Planetary Science Forum or join the Moon's Facebook group. And I think that is it. Good night and thank you. Bye.